one meaning, and later we assign weights to the edges of this graph. The weight is the similarity between two words. So I want to know the similarity between go and survive versus go and die, for example. And later, out of this graph, we select a subgraph using our secret key. So it is harder for the adversary to figure out what we have used for embedding. And also I color this graph, the small graph, with 3 colors, because I have 3 roles for every word. One of them is carrying the bit 0 or bit 1, or maybe it can be non-encoding. And also I have to also deal with some constraints. The other constraint I have is, given a synonym set, given a word, I want to have equal probability for embedding 1 or 0. So I want to divide its synonym set into equal number of 0 carriers and equal number of 1s. So the coloring has to take care of this constraint too. Another thing we wanted to achieve here was quantifying the distortion. As I have told you, the author might say, okay, I don't care if you can embed 5 bits, it's enough for me, please don't change too much. And he can set a lower threshold for distortion, because when I am replacing, I'm putting in some distortion to the text. Also, another distortion we want to quantify is when an adversary wants to undo our changes, I want to maximize his expected distortion. As I have said, we want to embed the watermark so that the adversary will reduce the value of the text when he's trying to change it. So what happens is, when there are more than one alternative to insert one bit, we pick the one that is staying below the author's threshold, the embedding threshold, and maximizing the expected distortion of the adversary. And I will give you an example of how we do it. Let's say I want to replace the word operate, and both go and run can insert the bit that I want. Let's say it's 1. You see here the weights, and for simplification, every synonym is just one distance from its synonym. So every one in the same set is just one distance. The edge weight is 1. But we don't care about when we are quantifying the adversary's distortion. We care about the distances of the candidate. If I pick run, for example, my candidates will be, for the adversary will be move, escape, or operate including. I want it for him to be hard to find that my original word was operate. I want to increase his uncertainty about what was the original word. And given these distances and the number of neighbors, our candidate is run instead of go to replace operate with, because it will make it harder for the adversary to come back to operate. And this is another system that we have built. Here the aim is we are moving into another field now. Here all this talk, I have been talking about grammatical text, the text that has high value, the text that has style. But the daily exchange text does not have those properties. It's a cursory text. Mainly you write email, when you're writing emails or SMS, you don't care whether it is grammatical. If you can pass that, hey, meet me at 6 p.m., that's enough for you. You don't care whether there is a typo in that message. So this creates another channel for information hiding, because typos can occur in any part of this document, and usually humans adapted to these errors, and they can really perform very good spell correction. So we can use these changes to embed information. In fact, it is not only typos. As you can see some examples on the bottom. The first example is a typo, but the other one is an acronym that people use very commonly. It stands either for lots of love or lots of love, or the lead speak, if you know. Every character has another matching in the lead speaks. This is also something very commonly used, or the smileys, or the colloquial language. And even DCT, it means discrete cosine transform in one area, or divine command theory in theology, I think, as far as I know. So what we did was, the challenge we had was powerful spell checker. So I have inserted errors in my text to insert my message, but then a spell checker can come and, hey, this is wrong, and can ask the author to fix it, or automatically can fix it and remove my watermark or my steganographic message. So what we decided to use was using ambiguous or stealthy typos, or both of them together. What I mean by an ambiguous typo is, for example, I'm given the word world, and I want to change it to a typo of it. I can pick world, which is very close to wood, word, and world. In fact, I picked them from Microsoft Word. If you write it this way, at least my version, gives all three options. It doesn't even give a, like, which one is more probable. It just gives them equally probably a fix of the typo borrowed, which is an ambiguous typo, which will confuse the adversary. The other typo that we need for an active adversary in the case of watermarking is a stealthy typo. For example, I can receive this sentence in an email, don't forget to bring the cake. I can change it into sake, which is a dictionary word, and which is totally meaningful. But since I know the communication between me and my friend, I will be able to figure out, hey, I'm bringing the cake. Like, it's not the sake. And this is impossible for a spell checker to catch. Unless they're using some like language models, unless they know the communication between me and my friend. Another thing that we have not implemented yet, but it's a like area that we can go in. There are two-way ambiguity in these documents. For example, GBH stands for Great Big Hug, Grievous Body Harm, which is like totally different meanings. Or you can rewrite good to see you in like 4 different ways that I have seen, in fact, more ways. Like another way for ambiguity. And this system also lets us apply some heuristics when we want to increase the ambiguity of the attacker, the adversary. We can either maximize the adversary's uncertainty about the original word, where we use the entropy. So if the candidate word has a higher number of synonyms, like the example that I have given you, it's better for us because it will be harder for the adversary to come back, as you have seen in the example. But I can do another thing. I want to maximize the probability that if the adversary randomly changes some of the words to their synonyms or to their typos, he will stay on the same bit. So he has replaced by my bit carrier, which was carrying 1, with a synonym. But if it is still carrying 1, he didn't really do any damage to my watermark. This work also appeared as a paper at like SPY 2007. Okay, so I want to mention a few things that I have told you about and some of the impact of this work. I have presented to you 3 different approaches which are equally powerful and which have assumed different scenarios. The first one is like Equmark, the sentence level watermarking one. The second one is Equmark, which is using robust synonym substitution. And the third one that you have heard is Markerr, which is ambiguous errors that you embed into cursory text. We have covered several types of text, like short text, long text, edited text, or cursory text throughout this work. And also we have, you were like, I wasn't able to give you too much details, but one of the concerns we had was a light mark detection process. Because there is this thing about watermarking. If you watermark an image, a photograph that you have taken, when you put it online, how will you be able to find that somebody else has put it on their web page? You need, for example, Equmark uses robots that are going around, checking every image and trying to figure out if there is a watermark on it. So the detection process needs to be light so that these robots can go around without disturbing the communication of other people and figure out whether there is a watermark on the displayed image and that the domain of that image is not your domain. You don't like own that domain. So we need all these systems take into account that the detection, the watermark extraction, is a light process. This is a challenging problem. Like as I have told you, there are many challenges included because we are working on text, and also there are many challenges involved in information hiding. There are a lot of application areas for this. Like you can, as I have said, you can try to watermark your emails, or you can try to watermark your articles. And there are many applications why you want to do that. And another thing that we have done is we have increased the interest in the research area. So we are known as a Purdue group who is dealing in natural language watermarking, but there are many people who are who have started to work on natural watermarking because we have been publishing, we have been sending people like emails about these conferences where they can publish. And as a future work, we want to work on the applications where we have a system that uses natural language watermarking to deal with a problem that the system has. We want to improve the evaluation techniques. So when I create a